Thanks for the introduction. I'm Pieter Meiresone. We are both from the Image Processing and Interpretation Group, actually, from Ghent University. And today I will talk about object detection for event cameras. So event cameras, they promise us the capability to have ultra low latency and high dynamic range, which could be very interesting for automotive applications, especially for autonomous driving, for example. We all know the situations where when we're driving at sunset and there is lens flare in our eyes, our vision is impeded, and as well the computer vision algorithms, they might also suffer from this in their performance. You see here there is a car in front, but there is actually also a car here exiting its driveway. So it is interesting to look in these scenarios where those performance could be improved. We also have, for example, the scenario when we're driving in the evening, that because there is less light, there is increased motion blur, and the computer vision algorithm might miss the second pedestrian here who is in the intersection. In our group, we mainly focus on the automotive application, but we also look at the extensions to other domains where this camera could be used, for example, in drones or in robotics. So first I want to recap a little bit the working principle of an event camera or a dynamic vision sensor. So in the typical standard camera, we know the pixels are, the points are collected on every cycle, and every frame cycle, a full image frame is being outputted. In a DVS sensor, this is completely changed, and there in the sensor, each pixel is considered independent and also asynchronous from each other. So the output is just a sequence of events, a continuous almost stream of events, where each event that is being triggered indicates that in a certain pixel location in the image frame, brightness change has occurred. This is actually the property which results in the high dynamic range for the event camera. So each event is represented as a pixel. It has a pixel location in XY, and it also has a polarity attribute which indicates that if it's 1, which indicates that the brightness has increased, or 0 if the brightness has decreased. So you see here in the example that the standard RGB camera would suffer from motion blur when there is a lot of changes in the scene, and the DVS would just output more events without losing the accuracy there. So it's also interesting to look at the current hardware for DVS cameras. Well, in a typical RGB camera, you would have like 80 plus minus, depending which sensor you look and which mode, 80 dB dynamic range, and you can already go up to 4K resolution and beyond. But for an event camera, we were until recently quite limited in terms of the resolution, where we would have like 346 by 260 pixels, but they have an increased dynamic range. And recently, we can now also enjoy the HD resolution in event cameras up to 720 pixels. And then the event stream can be up to more or less 1 giga events per second. In the meanwhile, we also have a very low latency, below a millisecond, which is very difficult for the RGB cameras to compete in the consumer segment. So then we also have chosen these event cameras specifically to our interest because they also have public data sets available for the automotive use case. So the first one is called Gen 1 from the first generation event camera, and the other one for 1 megapixel event camera. You see that the first one still suffers from quite some noise, but the second camera basically has no noise anymore, not visible at least. And you see immediately also the difficulty of working with the event camera in case that there is no changement in the scene. It triggers also no events. So this is then an interesting challenge to make it still work for object detection. So we consider specifically the cars and vulnerable road users, such as pedestrians and cyclists. The 1 megapixel dataset has 25 million bounding boxes, so it's quite a lot, which can be used for neural networks. So you see here that the bounding boxes are labeled and visible, and yeah, there are no events being triggered. I should specify what we use an event frame representation here, where we show positive events as green and the negative events as red, and they're collected between every frame cycle. This is just chosen this representation because it's more visible like that, or more interpretable like that for us, instead of showing the direct event point cloud. So we should also look a bit into the current state of the art, which is used for event object detection. So actually, it would make a lot of sense to use spiking neural networks, because it corresponds directly, the spike trains that you have to input in a spiking neural network correspond directly with the event stream. And there exists already spiking variants of common object detectors, but since their performance is not yet on par with their counterparts, we have chosen to try to use the performance of like the current YOLO detectors instead of going to a spiking neural network. There are also other methods which try to aggregate the events in some sort of feature. For example, here they use a histogram between each frame cycle. There are others that also use hypervolumes, where they don't discard any information and include an extra dimension or dimensions for the polarity as well as the timestamps of the event, and then pass this cube or hypercube through the neural network. The current state of the art, actually, these are both. This one is actually more state of the art than that. It surpassed it, but they use a similar kind of structure. So it can actually be subdivided into different parts. So the first part of the neural network is actually responsible to create an event frame, like the representation that I've shown here before, but optimized for the object detection task at hand, which uses here transformer layers as well as conventional convolutional neural network layers. They also include recurrent neural network layers to act as a memory function between the different frame cycles for the events to pass the information to the next event frame. In this case, on the right, they use the LSTM layer. And then finally, the third part, you have the detector backbone, which is your favorite backbone that you can choose, BGG or YOLO or others. And then they combine it everything, and they train the entire pipeline end-to-end on the event data. So here, you should also specify that you start from the sparse event point cloud. What we propose is follows a similar structure. So you also have a part where you construct your event frame, and then you have the second part, your object detector. And what we propose is a fixed representation here that we decided, where we have 3 different channels that are passed into the object detector, where the different channels act as different memory functions. So we have a short memory channel as well as a medium and a long-term memory channel, where one is for fast-moving objects until the last one, which is then basically used for the static scene. And we use this by decaying the event intensity from the previous frame cycle. I reuse it in the next frame cycle, but the event intensities, we decay them via an exponential function, which is shown here. This is actually similar to how actually a spiking neural network works for the activation of the neuron. They also use an exponential function to decay the activation in the neural network. So here I have shown how this then would actually look for 2 events. One positive event and one negative event. I've just shown them in the same image and how they would map into our RGB image basically. This is for 3 seconds, and this is for the decay until 30 seconds. So you see that the decay for an event in the short and the fast channel would disappear almost immediately, while in the slow channel it will remain almost indefinitely until it is replaced by a new incoming event. And then our different channels would look like this. So here we have the fast-moving objects. If there is a lot of movement in the scene, this completely disappears when there are no more events. But in the right channel, it stays visible. So by constructing this representation, we assume that, for example, a YOLO detector should still be capable of then detecting still the truck and the car in the scene. And then after retraining the YOLO detector, we can compare our performance to the current state of the art, for which we use the COCO evaluation metrics. On the Gen 1 dataset, we obtain a performance which is more or less similar compared to the current state of the art. And on the 1 megapixel dataset, we outperform the feed-forward representations, but not the current state of the art, which uses the more optimized event representation. But I hope this paper can show that we can still obtain performance improvement by using very simple constructs, and by using it this way, it's easier to train. It bridges the gap towards the use of the more complex methods. I also included the impact of the different memory channels by including the different time constants we have, which results in an actual increase of MAP on the dataset. So then I want to end with this video where I demonstrate the detector. So here we have the normal, we have the visualization of only the events, so that you see with the ground truth labels. So you see then on the right the result of the object detector on our event frame representation, and you see that the cars that are here parked, even though there are no events registered, they are still being detected. I also took this example because you see that the car in front is actually not being detected, although these here are. So I guess, for example, here the lights of the car still confuse it somehow. This is something that can be still optimized, I guess, in the future. So this was everything I wanted to say. Thanks for your attention.